Hello everyone. Very happy to join the MedShapeNet workshop at MICCAI2024. My name is Yucheng Tang from NVIDIA. Today I'm going to talk about the efficient computing of 3D medical imaging data, so the MONAI's open source models, frameworks, and platforms. So NVIDIA is at the heart of medical AI advancement, and currently we are building many platforms and tools and algorithms. So you may know that for MONAI, which is a medical imaging algorithm platforms, and also we have the InViFlare for predictive learning, and HoloScan for medical devices, and Parabricks and BioNeMo for large language models. Today I'm going to focus on MONAI side, which we are featuring the research and industry standard software for medical image analysis. So 3D models, especially the medical healthcare data, have revolutionized healthcare by providing precise representations for patient anatomy. And it can provide capturing complex shapes and volumes which are critical for access the diagnosis and personalized treatment. And one of the breakthrough in this area is leveraging the datasets like MedShapeNet. Currently, we have a larger and larger scale repos of 3D anatomical shapes and datasets, which can provide us and enriches our ability to model and understand the anatomical variations. And these detailed models combined with the foundation models that are pre-trained on vast datasets can create a powerful framework for various medical imaging tasks. Inside NVIDIA, we have the research projects for 3D volumetric networks. We have multimodal applications. Also, we are targeting like foundation models for computer vision in healthcare and medical imaging domain. I will cover that later, but you can see that like currently the 3D models can cover more and more anatomies, such as the whole body scans and whole brain scans. Building on this foundation, so we propose our state-of-the-art models starting from 2022 with UnitR. The UnitR is a transformer-based model, which has a VIT-based model for its encoder, which can bring us an innovative approach to learning the long-range dependencies in 3D volumetric data. And afterwards, we proposed the swing UnitR, which build on this by integrating a powerful swing transformer architecture and allowing it to capture both global context and local details with a remarkable precision. And then, so we further optimized the performance on the swing UnitR by integrating some like convolutional layers within its vision transformer encoders, which has achieved even greater accuracy and generalization across the multi-organ segmentation tasks. And these models represent the cutting edge of deep learning in medical imaging, which can offer us the unparalleled capability in organ and tumor segmentation. Well, it can drive driving forward the potential of AI-powered diagnostics. During the research of the swing transformers we conducted several years ago in NVIDIA, so we figured out that the fully supervised convolutional neural networks have dominated performance in the past few years, which drives a challenge of utilizing the representation of the large-scale for medical data. And annotating the large-scale 3D medical datasets is extremely challenging. So we know that the MedShapeNet did a really good job at creating these vast amount of shapes and labels for 3D images, right? But compared to the CNN-based counterparts, the transformer-based models, which can learn stronger features representation during the pre-training. So we proposed a framework that can featuring the pre-training algorithms, drive the motivation from the computer vision and natural language processing, that we collected a large amount of unlabeled medical image data, especially CT images, that can power us the ability to learn medical image representations. So, motivated by this and tackle the limitations from the CNN, so we observed the human body, which can present a naturally consistent contextual information in graphical images. And these proxy tasks can be utilized for learning the underlying patterns of the human anatomy. For this purpose, we extracted numerous patches from the 3D CT images from different regions of interest, such as the head and neck, lung, abdomen, pelvis, to learn this robust feature representation. And from various anatomical contexts, organs, and tissues, and shapes with a diverse set of human body compositions, we build a pipeline and workflow to learn the general purpose representation from different institutes' data. And here you can see that we propose and introduce our novel self-supervised learning framework for 3D medical image analysis, utilizing the transformer models, which is pre-trained by the SwingNet-R model. And we show the visual comparison afterwards using the pre-trained SwingNet-R model with the prior state of the art. You can see that we particularly highlighting the improvement on the small tissues with spatial context, such as the pancreas tails, branches in the portal vessels, and the adrenal glands which we are achieving like a better segmentation visualizations here. We also feature the SwingNet-R model that can achieve generalizability across different targets and anatomies. Back to 2022, that we achieve like a state-of-the-art performance on the MSD datasets and challenge here by segmenting very good performance on the tumors like the liver and tumor, the lung lesions, and pancreas tumor, and the others. Okay, so that's the work from 2 years ago, published in CVPR 2022. And in very recent work, we focus on foundation models that can utilizing a single model that can segment like as much as possible the targets, right? we know that total segmentator paves the way of annotating more than 100 anatomies and organs, which is a very good data set. By leveraging that and many other public data sets, we collect a partially labeled collection of datasets into our training segmentation pipeline for 3D volume medical image data. We call this work Vista 3D in terms of the versatile imaging segmentation and annotation model. For common classes here in this model, so we have enough labeled from the model training, such as the total segmentator or other MSD datasets. And also we have the zero-shot capability integrated into the model using the minimal annotation efforts. And with a few annotated examples, users can fine-tune the model and continue the steps in order to support this. So this is a performance we proposed and published recently on the comparison, on the quantitative comparison between the Vista 3D model with the AutoML pipelines such as the Auto3DSeg and NNUnet. And also we proposed the raw NNUnet pipeline trained on the total segmentator and comparison on the test set. So next model I want to highlight here is called the MICCAI. MICCAI represents the medical AI for synthetic imaging, which we are leveraging a 3D diffusion model that can generate a whole volume of CT images. MICCAI can address some of the biggest challenges in medical imaging today, which are limited access to annotated data, high costs, and privacy concerns. And building using the diffusion model, so MICCAI generates high-resolution synthetic 3D CT images that includes detailed labels for up to 132 anatomical classes. And this synthetic data helps augment datasets where real patient images are scarce. which can provide us like diverse and realistic images that are increasingly valuable for training machine learning models. And one of the most powerful features of MICCAI is its ability to generate paired image and label data for organ segmentation or tumor detection tasks. And this reduces the manual labor needed for data annotation and allow researchers to create more robust and generalizable AI models. And it is an ethical and scalable solution that doesn't rely on sensitive patient data for privacy concerns. And yet also we can improve the accuracy and realism. Yeah. And ultimately, MICCAI's capability can generate high-fidelity images and leverage its potential to integrate with existing frameworks like MONAI's, like open source side models that can you can use it for the downstream segmentation tasks to generate more training data. Yep. So that's the several models that I want to highlight in this talk. And next, I'm coming to the platforms and frameworks that we proposed and created inside NVIDIA with the MONAI, which are fully open source. So MONAI is represented as the medical open network for AI, which is a open source framework that has become the foundation of AI-powered medical imaging research and development. It provides a comprehensive suite of tools and specifically designed for healthcare applications such as the radiology, pathology, or even endoscopy or like surgical tools. And what makes MONAI stand off is flexibility. So as it is fully open source, and the platform supports everything from simple workflows to more complex tasks such as the segmentations, no matter it's 3D or 2D, or even federative learning frameworks. Its integration with the popular AI libraries such as like a PyTorch or even others like scalability and its performance. Well, recently we also integrated Hugging Face applications here. Well, it's deep integration with the NVIDIA stuff, and also throughout tools like MONAI Deploy and also the Clara Holoscans. We have a lot of downstream deployments for using the open source MONAI side, which allows for the real-time inference and cloud-based deployments. MONAI also have many like modular design components, which allows users to customize their pipelines from data processing to model training or validation, or even to create a new annotated datasets. So as I know that MedShapeNet, some of the datasets inside this large scale data collection is annotated by some MONAI components here, which we can like adapt to a variety of research and clinical environments. Another thing I would like to highlight here is the how we can integrate the AI assistant annotation for medical imaging data, like using MONAI. The AI assisted annotation tools are playing a very vital role in reducing the efforts required for manual data annotation, which has historically been one of the most time-consuming aspects of medical imaging projects, like many hospital and medical centers, which requires like a lot of manual efforts to tracing those medical images. And now these AI assisted tools like can integrate a component from MONAI can help automate the annotation process and leveraging pre-trained models for to label the medical images, such as the segmentation organs or detecting anatomies. And by using AI-driven methods to generate high-quality annotations, and researchers can significantly accelerate the model training process while maintaining the accuracy. And this reduce the need for expert manual labor, and speeds up deployment for AI models for clinical use, and enabling faster data analysis and ultimately bring innovations to healthcare faster. And in particular, so we built a tool inside MONAI, the community, which is called MONAI Label. MONAI Label is the open source tool that accelerates the process of annotating medical images by providing the features of a backend server, a very lightweighted backend. It integrates the stimulus with popular medical imaging viewers such as the 3D Slicer or OHIF or other pathology or endoscopy viewers. And this significantly reduced the manual efforts required to annotate large-scale datasets. And MONAI Label supports real-time iterative learning capabilities, also active learning, and making it a dynamic and powerful tool for both research and clinical applications. We have a lot of collaborators using MONAI Label to create their own customized datasets and to label, to create labeling workflow for radiologists or clinicians to make their own datasets to train their AI models. Yep. So very recently, NVIDIA also introduced our a healthcare microservice suites, which is designed to streamline the deployment and management of AI-powered medical applications. We call it NVIDIA NIM in terms of NVIDIA Inference Microservice, which is a set of easy-to-use, very lightweighted, self-hosted microservice that can enable optimized inference for a wide array of AI models in the medical imaging. And this microservice makes it simpler to integrate AI models into healthcare workflows, offering the scalable solutions for inference deployments and management. Here, we provide the Vista 3D NIM here. If you are interested, you can open the link here in this slide, and which is fully free and open to the public, that you can play with the microservice. We build some cloud-based APIs using the backend from NVIDIA Cloud Service to deploy the AI models featuring A100 GPUs with this Vista 3D model we built inside NVIDIA. And also we have the MICCAI NIM, so you can play with it by providing some parameters like what you want to generate, such as the CT, like a body region or an anatomy list that can provide a generation of a CT volume and with its segmentation labels. Yep, you can open and go to the buildnvidia.com. You can find these two models from the healthcare domain. To do some diffusion models like MICCAI and the segmentation model like Vista 3D. Yeah, I think that covers most of my talk today. I would like to highlight here that MONAI and MedShapeNet, the team has already built a very cool stuff and amazing projects that represent the future of AI-driven medical imaging and forward the projects and models and datasets specifically. And MONAI, with its open source modular framework, empowers researchers and developers to build advanced AI models that hopefully can tackle complex medical imaging challenges like segmentation, classification, and vector learning, especially their workflows and deployment. On the other hand, I think MedShapeNet also provide a critical resources with an extensive 3D shape dataset derived from the real patient imaging data, which is very valuable, allowing the researchers to push the boundaries of shape analysis in medical contexts. And by integrating these two resources from MONAI and MedShapeNet, I believe they are fully open source. And that paves the way and opens the door to many possible applications and powerful generalizable AI tools for accurately understand and analyze the intricate anatomical structures captured in medical images. I believe that the MONAI and MedShapeNet both are the advanced tools and resources and datasets that we can use to drive our insights and better clinical outcomes and advancing both research and real-world medical applications. Thank you so much for the talk invitation, and very glad to be here. Even though I'm not able to join on-site, I'm always here. If anyone have any questions, please let me know, or even send me emails. Thank you so much, and these are some resources. You can find the links in the slide. Thank you.